Now that we know that two fractions that look completely different could possibly be equal or equivalent, we might come across problems that asks us to determine whether two different looking fractions are in fact equal. We've got three ways to do that. The first way is to write both of the fractions in simplest form. So if we're looking at 12 over 42, I'm going to factor 12 completely. I know it's the same thing as 2 times 3. And then 42, I know that that's 6 times 7. So that's 2 times 3 times 7. And I'll divide off the common pairs from the top and bottom. So 2 over 7 is the simplest form for 12 over 42. And then let's look at 10 over 35. 10 is just 2 times 5, and 35 is 5 times 7, so we can divide off the 5's, and we get 2 over 7. Now, the simplified version of each fraction comes to the same value, therefore we know that they are equal. 12 over 42 is equal to 10 over 35, because in simplest form, they're both the fraction 2 over 7. Another way to do this is to find a common denominator between the factors. Now, finding common denominators really means look at the two denominators and find the least common multiple. Now, in reality, it does not have to be the least common multiple, it just needs to be a multiple. So we could do 42 times 35 and use that as our common denominator. But since we already have each number factored, it might be easier to find the least common denominator in this case. So we have 42 is 2 times 3 times 7, and 35 is 5 times 7. They both have a 7 in common, so our least common multiple is going to look like 2 times 3 times 5 times 7. I know 5 times 7 is 35, and 2 times 3 is 6. So our least common multiple, which we'll use as our least common denominator, is 6 times 35, which is a little bit smaller than 42 times 35. It's 210. So if we wanted to write 12 over 42 as an equivalent fraction over 210, remember, we did this before. We just needed to find 42 times a special number, gives us 210, and it turned out to be 5, the special number. And then 5 times 12 was our new numerator, and that was 60. We'll do the same thing for the fraction 10 over 35. We want to rewrite it as an equivalent fraction with the denominator of 210. So we're going to look for a number that we can multiply by 35 to get 210. It's going to be 6, because 6 times 35 is 210, which means 6 times 10 is our new numerator. Notice that when we wrote the two fractions so that they had the same denominator, their numerators also matched. So this is another way to show the two fractions that look terribly different are actually equal. We have one last method, and that's to make an equality and then try to manipulate that equation to show a clear true or false statement. So if we have 12 over 42, and I'm going to test this equality, so I'll put a question mark above it. I want to know if that's equal to 10 over 35. And what we'll do is multiply through by each denominator. So I'll multiply both sides by 42. On the left, the 42's divide off, but on the right, the 42 sticks around. I'll do the same thing with the denominator of 35. This time, the 35 on the right divides off with the denominator, but on the left, the 35 sticks around. Lots of people like to call this cross-multiplying because it looks like I took the denominator from the left and multiplied it up to the top, and the denominator from the right and multiplied it up to the top. But technically, we're just multiplying through by our common denominator. Sorry, not the common denominator. We're multiplying through by each denominator. Our result then looks like 35 times 12 on the left, and we're trying to see if that is equal to 10 times 42 on the right. Again, we'll use our calculators here to help us out. 35 times 12 comes out to 420. 10 times 42, well, that also comes out to 420. So it's true, we can use this equation to justify that the two fractions were equal, because when we multiplied through by the denominators, we got a true statement. If these two fractions were not equal, then we would have a different number on the left side of this equal sign than we have on the right. Now let's talk about ordering rational numbers. We know that some rational numbers are larger than others and some are smaller than others, and now we know how to tell when they're equal to each other, but we might also need to decide which ones are bigger. For example, Jim claims that 1/3 is larger than 1/2 because the shaded portion in the diagram for 1/3 is literally larger than the shaded portion for 1/2. How can we possibly help him? Well, in this picture, the diagram that represents 1/3 is clearly larger in every way than the diagram that represents 1/2. But if we wanted to shade in 1/2 of this circle, we would have to shade in a much larger piece than the 1/3 wedge. And if I wanted to make 1/2, this rectangle, into 1/3, I would need to cut it into 3 pieces, not 2. So I could see that 1/3 is smaller in this case. So my suggestion for helping him would be to kind of transpose the fractions into each of the diagrams so that you can see comparatively which one's bigger or smaller. Without using a picture, we can order rational numbers depending on what the fractions look like. If they have the same denominator, then we just compare the numerator. However, if the denominators are different, then we can create this inequality statement and test to see if it's true. So for example, we have 4 fractions at the bottom of the screen, and we can test to see which ones are larger. We can do 4/5, and we're going to take a guess maybe that it's larger than 3/4. Well, if it is larger, then when we multiply through by our denominators, then we'll get a true statement. If it is not larger, then multiplying through by the denominators will give us a false statement. Well, look at that. We have a true statement. So we know that it's true that 4/5 is bigger than 3/4. And we can repeat this process for the other groups of fractions until we find which one is the biggest and which one is the smallest.